Hello everyone. This week you will be introduced to the 4-step travel demand modeling framework. Why is it called 4-step and what are the 4 steps in the modeling framework? As we discussed before, transport demand is derived and it follows a behavioral paradigm, meaning that there are a lot of human and behavioral factors involved in transport demand. Transport demand is derived from the demand to participate in different activities to satisfy needs. The goal in travel demand modeling is to estimate or infer the amount, type, and location of travel or trips from the spatial distribution of activities. The travel demand analysis relies on knowledge of where individuals, businesses, and shops and other places of activity, whether it's a gym or restaurant and other places, are located or will be located in future. The way we usually forecast travel demand is based on the location of these activities. And also, we need to know about the performance of a region in future from an economic and demographic perspective, how the region is likely to perform from an economic point of view, and the anticipated macro changes in the demography of the region. So for example, if one certain area of the city is going to have a lot more jobs in future, that will affect the travel patterns in the city. Same thing with demography. If one certain area of a city is going to be populated with a lot of young population, it will definitely affect travel patterns throughout the city. So let's start with the framework of travel demand forecasting. There are a couple of steps in this framework and we go through them. The details of each step will be covered in the coming weeks. So the first step is to obtain some information from the regional economics to better know how the region is performing from an economic and demographic perspective, as we discussed, both in the base year, whether it's current or in some previous time periods, and the horizon or the year that we are interested to forecast. After we gain some information about the economic and demographic perspective, from that information we estimate the sub-regional distribution of population. So we estimate how many people live in different areas of the city. And that estimation is usually done, that estimation of population is usually done by income level. So we know we also get to estimate the distribution of the income levels in different areas of the city. Next step is car ownership. After we know how many people with what levels of income live in different areas of the city, we model or we predict how many of them have cars, how many cars each household have. In fact, this car ownership level can actually move a little bit downward too. We will talk about it later, but you can do that in a different stage of the framework. The main part of the framework is what you see in this slide, where we have 4 key steps, which is trip generation, trip distribution, mode choice, and traffic assignment, and most importantly, a feedback loop that connects traffic assignment to trip distribution. And that's why 4-step travel demand modeling is called 4-step, is because of these 4 steps of trip generation, distribution, mode choice, and assignment. And at the end, from that 4-step framework, we get estimated volumes on the roads and estimated travel times. When we get those, from those travel times and volumes and the general model, we can study the social, economic, and environmental impacts of various planning scenarios. For example, if you want to increase the population in one side of town, what is the impact on the travel patterns? What is the impact on link volumes and travel times? If you want to increase number of jobs in another part of the city, what is the social and environmental impacts or the economic impact? What are the new link volumes and new travel times? 4-step travel demand models are a kind of zone-based or aggregate models. The zones in an aggregate model represent areas of similar land uses, whether it's residential, industrial, or shopping. In each zone, we need the forecasts of the population, employment, and retail space. Generally, we need a lot of land use information in each zone to be integrated in the travel demand model. There is a big assumption here in the travel demand model, in aggregate travel demand models, that all the activities in each zone are concentrated at a node or at a point, where we usually call it centroid or zone centroid. It doesn't have to be the center, at the center of each zone. It's only a node or it's only a point inside the zone. It could be anywhere. But the assumption is that all these activities, all the trips that gets generated and attracted to a zone will be concentrated in that centroid. In a travel demand model framework, we also represent transport infrastructure by a network of facilities that connect centroids to the network. So the network is actually described by a system of nodes and links, where nodes are usually the intersections or junctions, and links represent the streets connecting intersections. And we will have some dummy links, or sometimes we call them connectors, connecting the centroids and the network, whether the centroid getting connected to a node or the centroid getting connected to the middle of a link. I think with this representation that you see in this slide, you can get a better idea of what I'm talking about here. So imagine this is a city. We divide the city into different zones of homogeneous characteristics. For example, zone 1, zone 2, zone 3. Each could be residential or commercial, industrial, or mixed with some certain land use and certain number of populations and jobs in them. Inside each zone, we have a centroid. We specify a centroid, which is represented here as a triangle. Then we have the links and the nodes, or the road infrastructure, represented by a network. So you see all the nodes representing junctions or intersections, and links connecting them representing streets. And there are some tiny dashed lines connecting centroids to the network. In this example, centroids are connected with connectors or dummy links to the nodes, but it doesn't have to get connected to nodes. It could be connected to the middle of a link. So this is the first step of a travel demand model development process, where you create this representation, you create this network representation of your city, and then you go to the next steps, which is the trip generation, attraction, and etc. In the trip generation step, we predict the number of trips that will be originated. We also call it productions, usually represented by the letter P, or terminated. We also call it attractions, represented by A, in each zone. Trip generation, or the number of trips, whether it's production or attractions, is a function of the characteristics of the zone, usually the land use of the zone. For example, if one zone is 100% residential, what do you expect in terms of trip generation from that zone? Well, we expect to see a lot of trips getting generated in the morning, people going to work, and an opposite in the afternoon, a lot of trips getting attracted to that specific residential zone, people coming back home from work. Another example is if a zone is 100% industrial, for example, in the morning, there will be a lot of trips getting attracted to that zone, people going to work, and in opposite, in the afternoon, people coming back home from work, there will be a lot of trips produced or generated from that zone in the afternoon. After we know how many trips will be generated or how many trips will be attracted to a zone, next step is the trip distribution step, where we match these trip productions and attractions to yield a full spatial pattern of trip making. So now, after I know a number of trips will be generated from a zone, the question is, where will these trips will go? If I know a number of trips getting attracted to a zone, as another example, the question of interest in trip distribution modeling is from what zones these trips will be attracted from. So what is important in the travel demand modeling framework is the prediction of the travel volumes. Travel volumes, or the number of trips going between I and j, is the outcome of the trip distribution model, or we call them interzonal travel volumes, usually represented as Tij, where Ij represents the zones, T is the number of trips. So Tij is predicted as a function of the trips produced in the origin zone, trips attracted at the destination zone, some measure of the travel cost and travel time associated with the travel between zones I and j, and also comparative attractiveness of the competing zones. So that's the outcome of trip distribution model. The next step in the 4-step model is mode choice model, where we are interested to predict the travel volumes by mode. So after we know certain number of trips will be happening between zone I and j, we are interested to know their mode split. We want to know what percentage will take private vehicle, what percentage will take public transport, what percentage will take, walking and biking. So that's where mode choice comes into the play. So these models consider time, cost, other characteristics of each mode, characteristics of the traveler, sometimes land use characteristics, to determine what proportion of travelers will choose each mode. So then we can revise that Tij to Tijk, representing the number of travelers going from I to j by mode k. The next step in travel demand model, the 4-step travel demand model, is traffic assignment or route choice model. In this final step, the mode and time-specific trip tables are assigned to the network using a traffic assignment model, which essentially represents traveler's route choice. So for example, now that we know a number of trips are going to be made between zone I and j by private vehicle mode, we want to know what route these travelers will take. So from there, we can estimate link volumes, congestion on the roads, travel times. So the outcome of a traffic assignment model is the number of people traveling between node I and j by mode k using route t, a small letter t. So then we can revise that Tijk to Tijkt. Probably a very important step in 4-step modeling is this equilibration or iterative process that I showed in the framework earlier that connects the traffic assignment back to the trip distribution. So if I show it again here to you, so this equilibration process or iterative process is very critical in getting consistent results out of a trip model. So one of the inputs of the trip distribution stage is travel times between origin and destinations, between zones I and j. But at the beginning, we don't really have the travel times because we haven't yet estimated any traffic or travel times or any link volumes. So we start with some assumed travel times, usually free flow travel times between zones. And then we do the trip distribution, we do the mode choice, and then we do the traffic assignment. The outcome of traffic assignment is the updated travel times. So using that feedback loop, we go back to the trip distribution, we update the travel times as input of the trip distribution, and we repeat this process until the travel times that come out of the traffic assignment model step converges, meaning that they don't change much. They become a steady. This whole process is called equilibration or an iterative process in the 4-step model. And the step that we left to talk about is the car ownership modeling, which I briefly touched on. Before doing the trip generation, I said that we need to know what are the car ownerships. We use that in trip generation and the mode choice as well to know whether a household has any private vehicle available for them to make a trip. That really affects the mode choice model, because if a household does not have a vehicle, definitely private vehicle will be out of the options for them, and they will only have public transport, walking and biking, or maybe sharing a ride with someone. Car ownership usually gets modeled using aggregate time series, or using regression-based models, or discrete choice models, which are more accurate and popular. And this is what we will focus more in this unit in the coming weeks, the discrete choice modeling aspect. So the car ownership models forecast the total number of vehicles owned per zone. These zones in travel demand models, we usually call them TAZ, standing for Travel Analysis Zone. So in a car ownership model, we predict the total number of vehicles owned by each zone, or owned by each household, or even the fraction of households owning or having n number of cars, whether it's 0, 1, 2, or more. And car ownership models are often a function of household income, household size, how many members are in the household, or how many workers are in the household, type of residential, whether it's inner city, CBD, suburbs, and also land use and many other factors.